permutations with restrictions. And the first thing I have to do is I have to say sorry, because at the end of the last video I told you that in today's video we'd be learning about the next type of permutations question, and that's a permutations question where you had identical elements and you wanted to know how many permutations there are. For example, in the word sorry, if I want to know how many ways we could rearrange those, how many different words we could get by rearranging these, because we have the same letter twice, we have R here and we have R there, we have to take that into account, and we have to make sure we don't count the same word twice. I made a mistake. We're going to do that next day. First, what we're going to do today is we're going to learn about we're going to keep working with permutations, but we're going to start looking at restrictions on permutations. So basically, restrictions are often placed on the order in which the objects are arranged. So they're going to give you some kind of restriction on rearrange these objects, but you have to have the black object first, or you need to have the girls sitting beside each other, or you need to have the red ball last or something. Okay, you'll see. You're going to deal with the restrictions first. So when you're figuring out how to answer it, think about the restrictions first, then think about the other elements that aren't restricted. And you can usually solve these with the fundamental counting principle. I actually find it's often easier to use the fundamental counting principle rather than the permutation formula that we learned last time. So I kind of wish we'd done this section before last one, but this is the way it is in the book. Okay, let's get right to the questions. At a used car lot, there are 4 black cars and 3 red cars. How many ways are there to arrange all the cars if there's no restrictions? Okay, so the first question is nice. It's just, if there's no restriction, you can put any car first, any car second, any car third. What do you do? So basically, you look at how many cars there are total, and there are 7 cars. So if you want, you could think of it as, I have 7 spots to put those cars. 6, 7. How many possible cars could put in the first spot? Any of the 7. So you'd have 7 choices here. How many in the second spot? Well, we've already used 1, so you're down to 6, and 5, and 4, and 3, and 2, and 1. And what do you do with all those? The fundamental counting principle. The fundamental counting principle tells you that what you do is you multiply to get the total. Okay, the faster way, rather than writing 7 times 6 times 5 times 4, I could have just said 7 factorial. And if you do that, multiply those out, or put 7 factorial in your calculator, you get 5,040 ways. So if there's no restrictions, you would get 5,040 ways of arranging the 7 cars. Now we're going to do restrictions. We're going to limit some things. If we restrict what's possible, do you think there's going to be more or less options? There's going to be less, because this is all the possible options, and now we're going to look at just some of the options, because some of them we're not interested anymore. Okay, the next question is, the 3 red cars must be parked so that there's a red car at each end, and the third red car is actually exactly in the middle. So do you understand that? Let me draw my 7 spots again, 3, 4, 5, 6, 7. And what we're going to have is we're going to have 1 red car here, 1 red car here, so those are 2 ends, and a third red car exactly in the middle, so exactly in the middle will be right here. Okay, definitely I think fundamental counting principle is a good way to do this. How many cars can you choose from to go right here in this spot? Well, it has to be red, and there's only 3 red cars, so you can put 3 cars here. How many cars can you, we're going to skip over here, right? This is one of the restricted spots. So how many cars do you have to choose from here? Well, there were 3 red cars, but you put 1 there, so now there's only 2 red cars left. How many cars can you put here? Well, you've put 1 red car here and 1 red car here. There's only 1 red car left, and it has to go here. So it goes like that. Okay, now we'll go to this spot. How many cars do we choose from here? We're not putting red cars there, right? We're putting black cars there. Yeah, black cars there. How many black cars are there? 4. So you have 4 black cars to choose from here, 3 black cars to choose from here, 2 black cars to choose from there, and 1 black car there. And again, fundamental counting principle, we'll multiply all those things together, and that'll give us our answer. How could we write this in factorial notation? You could say, to place the 3 red cars, it's 3 factorial. And to place the 4 black cars, it's 4 factorial, and the fundamental counting principle tells us that we're going to multiply those 2 things together. So 3 factorial, 3 times 2 times 1 is 6, and 4 factorial is 4 times 3 times 2 times 1 is 24, and if you multiply those, you get 144. Wow, remember we had 5,040 ways to arrange the car, but if we restrict it in this way, we're down to only 144 ways to arrange the car. Okay, here's another restriction. The 3 red cars must be parked side by side. Okay, this happens a lot in these questions where they're going to tell you that certain things must be beside each other. So what a good strategy for doing this is to think of those 3 red cars that have to be side by side, kind of think of them temporarily as one element. So I'm going to make it a little bit bigger, this line, these lines I've been drawing, I'm going to make it a little bit bigger because remember, what goes here are 3 red cars, go right there. But I'm going to think of that as one element. And then how many other cars are there? Well, there's also 4 black cars, right? So I'm going to put 4 more lines. 1, 2, 3, 4. So if I think of this as one element, and then these are my 4 other elements, I have a total of 5 elements. And what I want to see is how many ways can I arrange those 5 elements? Because as long as I keep these 3 red ones together here, that's the whole goal. I have to keep them together. So as long as I consider it one element, they'll always be together. So how many ways are there to arrange those 5 elements right there? Well, that would be 5 factorial. But here's the thing, if you think about in here, you actually have 1, 2, 3 cars here. And it doesn't matter which one comes first, which one comes second, which one comes third, as long as they're all together. So now that we've placed this, think of it as a big element, we've placed it, 5 factorial, all the different arrangements that there are to keep those 3 red ones together. Now how many ways are there to place the 3 red ones when they're together? Well, in the first spot you could put any of the 3 and then 2 left and then 1, so you'd have 3 factorial here, and you multiply that together. Does this make sense? This 5 factorial is to place the 5 elements when you think of the 3 red cars as being one element. Then once we've done that, we have to consider just the 3 red cars and how many ways are there to place them, and there's 3 factorial for them. So 5 factorial equals 5 times 4 times 3 times 2 times 1, which is 120. 3 factorial equals 3 times 2 times 1, which is 6. And you multiply those, you get 720 ways of placing the cars so that the red ones are together. Okay, very similar here, but now we're going to put the 4 black cars together side by side. So just like we did above, remember how we thought of the 3 red ones as one element? This time we're going to think of the 4 black cars as one element. That's one element. Temporarily going to think of that as one element. How many other elements are there? Well, there's also the 3 red cars. So I got to draw 1, 2, 3. Okay, so think of this as one element, second element, third element, 4 element. How many ways are there of arranging those 4 elements? There's 4 factorial ways of arranging those 4 elements. But now that we've arranged those, we need to think of the 4 black cars and think, how many ways are there arranging those 4 black cars? Well, there's also 4 factorial ways of arranging those black cars. So you end up with 4 factorial times 4 factorial. 4 factorial means 4 times 3 times 2 times 1, which is 24. So you're doing 24 times 24, which is 576. Okay, last question of this, using the cars here, is the cars must be parked so that their colors alternate. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, it has to go red, black, red, black, red, black, or black, red, black, red, black, red. So think about it for a second. We have 4 black cars, 3 red cars. What does it have to start with? It has to start with black, right? If we started with red, it would go red, black, red, black, red, black. We only have 3 reds available to us. We'd have to put a black here, and it doesn't alternate now. So it has to go black, red, black, red, black, red, black. And this is a question very similar to what we already did. If we look at just the black ones, remember there's 4 black ones. How many possible black ones could go here? Well, any of the 4. How many here? Well, we've used 1 already, so we're down to 3, we're down to 2, we're down to 1. If you look at the red ones now, how many red ones could we choose from here? Well, there's 3 total, so we could put 3, but now we've used 1, so we're down to 2, and now we've used 2, so we're down to 1. And fundamental counting principle, multiply them all. Or the other way we can think of it is, to place the black ones, it is 4 factorial. To place the red ones, it's 3 factorial. 4 factorial, 4 times 3 times 2 times 1 is 24. 3 factorial, 3 times 2 times 1 is 6. Multiply those, you get 144. It's actually a really, really similar question to the one we did right up here. Okay, enough about red cars and black cars. Let's do different questions. Oh, we still have 4 of something and 3 of something. That's too bad. This time we have 4 books on math. Nice. And 3 books on English. Okay. And they need to be placed on the shelf so that the books on the same subject always remain together. So we got to keep all our math books and all our English books together. Okay, so it's kind of like what we did before, but this time we're going to keep all the math books together. So we're going to think of those 4 math books as one element temporarily. So 4 math. And we have our 3 English books, so we're going to think of those 3 English books as one element temporarily. And do we have anything else? No, that's it. So if we wanted to know how many ways there are to arrange these 2 elements, remember we're temporarily thinking of it as 2 elements. How many ways? Well, 2 factorial, because you could pick any of 2 here and then just 1 there. So 2 factorial. But now we got to think of the math books. There's actually 4 math books here. How many ways are there to arrange those 4 math books? That would be 4 factorial. We also have to think of the English books, because there's 3 English books here. How many ways are there arranging those 3 English books? 3 factorial. So we have to actually multiply 3 things together this time. 2 factorial times 4 factorial times 3 factorial. 2 factorial is 2 times 1, which is 2. 4 factorial is 4 times 3 times 2 times 1, which is 24. And 3 factorial is 3 times 2 times 1, which is 6. You end up, if you do that, 48 times 6 is 288. How many different 8-letter words can be formed out of the letters of the word daughter? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you got to use all the letters, and we're going to rearrange them. And the first way it says to do it is the word starts with a D and ends with an R. Okay, this isn't too bad. 8 letters. 1, 2, 3, 4, 5, 6, 7, 8. And it tells us it has to start with a D and it has to end with an R, but then it can be any other arrangement in here. So we've used the D, we've used the R. How many more letters are there to arrange? 1, 2, 3, 4, 5, 6 more to go. So this has to be a D. There's no choice. You have to put a D there. You have to put an R there. So if you want, you could put a 1 here and a 1 here to show that there's only 1 letter goes here and 1 letter there. Or you can just, fill them in with those letters, because they definitely go there. But of the 6 letters that are left, how many could go right here? Any of the 6. So you'd have 6 possible letters here, and then it drops down to 5, to 4, to 3, to 2, to 1. Multiply them all together because of the fundamental counting principle. So you end up with 6 factorial. And 6 factorial, 6 times 5 times 4 times 3 times 2 times 1 is 720. What if the position of letter H remains unchanged? Okay, so it's an 8-letter word, 2, 3, 4, 5, 6, 7, 8. And in daughter, the letter H is the 1, 2, 3, 4, fifth over. 1, 2, 3, 4, 5. So this has to be an H. But everything else can mix up as much as you want, put it wherever you need it to be. So we've used the H, but we still have 7 letters. So in this first position here, you can choose any of the 7. 7 times 6 times 5 times 4 times 3 times 2 times 1. You're not multiplying by the H. That's just, that spot's filled in. But you got to do all the rest. So you're doing 7 factorial. And 7 factorial is 5040. Okay, in how many ways can 5 children be arranged in a row such that the 2 boys, AJ and Sachin? No, I'd say Sachin. Who knows? They always sit together. Okay, this is, again, when you have elements that have to be stuck together, you want to think of it temporarily as one element. So let's draw our 2 boys here as one element. This is AJ and Sachin together. So that's 2 of the boys. There's 5 boys total, so you still have 3 more to worry about. So we're going to arrange those elements. Notice we're going to think of it as 4 elements for now, so that these guys are always together. We're going to arrange those 4 elements. How many ways are there to arrange those 4 elements? 4 factorial. But now we got to think of AJ and Sachin, right? AJ could sit before Sachin, or Sachin could sit before AJ. So you got to multiply that by 2, or if you want, 2 factorial, because 2 boys could go in this spot, only 1 boy could go in that spot, so 2 times 1. And that's it. So 4 factorial, starting to memorize all these. 4 factorial is 24, 2 factorial is 2, so you get 48 ways to place the boys so that AJ and Sachin always sit together. And now the most difficult question in the video here. How many ways can you arrange the 5 children so that AJ and Sachin never sit together? Now, one way you could do this is you could draw your 5 kids and you could start thinking of all the ways it could work. Okay, so if I put AJ here and Sachin here, and then the other kids would go here, here, and here, I'd have 3 factorial. Or I could put AJ here and sashing here, and I'd still have 3 factorial. And I could keep doing this and it would work, but it gets pretty complicated. But let's think of something here. If we already know all the ways that they can't sit together, these are all the orientations, the arrangements of the boys when they are sitting together, then if I wanted to know all the times they don't sit together, do you see what I could do is I could figure out how many ways are there total for the boys to sit if there was no restriction, because that's really easy to figure out. And then I could just subtract this amount and I'd be left with all the ones when they aren't sitting together. So let me go through that with you. Let's first of all find the total arrangements. So in other words, if there was no restrictions, how many ways can you arrange the boys if there's no restrictions? Well, there's 5 boys. You get to put them in any order you want. So the first spot could be 5, 4, 3, 2, 1. Hopefully by this point you get that there'd be 5 factorial ways of arranging the 5 boys, and that's 120 ways that you could do that. Now, these 48 ways, remember this is part of the same question, these 48 ways are all the ways that these 2 boys will be sitting together. But we don't want them to sit together. Well, if there's 120 ways that boys can sit and 48 have these 2 sitting together, then there must be 120 minus 48 ways that have the 2 boys not sitting together. 120 minus 48 is 72, and this is your answer. If it helps you, this is our total. This is sitting together. So if you take all the cases when they're sitting together and subtracting it from the total, then what you'd be left with is all the cases when they're not sitting together. And this is a strategy that does work sometimes. It kind of takes a moment of brilliance to recognize it, but if you do get stuck and you're finding you're having to do way too much work like I would have in the other method I showed you, ask yourself if you can find the total arrangements and subtract something else. It often will work. Okay, next day I promise we'll get to that third type of permutations. So enjoy your permutations with restrictions.